Earth, our home planet. A small blue world suspended in the darkness of space. Every human who has ever lived, every civilization that rose and fell, every culture, every language, every belief system, every conflict, every discovery, all of it unfolded here. From this single point in space, the universe feels vast, but it also feels measurable. We talk about distance, we talk about size. We ask how big the universe is, as if the answer is simply a number waiting to be calculated. It feels like a reasonable question. After all, we measure everything else. We measure the height of mountains, the depth of oceans, the distance between cities and continents. So why not the universe? But what if this question is misleading? What if the universe does not become difficult to understand because it is too large, but because beyond a certain point, the very idea of size stops making sense? What if the problem is not scale, but the limits of how the human mind interprets reality? This is not a journey meant to impress with enormous numbers or breathtaking distances. It is an investigation into where measurement begins to fail, where intuition breaks down, and where knowledge itself encounters boundaries. At human scales, size feels natural. We understand meters and kilometers because we can move through them. We understand cities because we can cross them. We understand continents because even if we never traverse them fully, they still fit within the span of a lifetime. Even space at first behaves in ways that feel familiar. From low Earth orbit, our planet is unmistakably spherical. The curvature of Earth becomes visible, gentle, and complete. From the Moon, about 384,000 kilometers away, Earth appears as a fragile disk of blue, white, and brown, hanging silently against a black background. The distance feels enormous, yet it remains imaginable. We can calculate it precisely. We can visualize it with scale models. We can plan a journey and understand what it would take in fuel, time, and engineering. At this scale, size is something the human mind can still grasp. Space behaves the way we expect space to behave, but this sense of familiarity does not last for long. As we move outward, the next major landmark is the Sun, roughly 150 million kilometers away. A distance so vast that light itself, traveling at nearly 300,000 kilometers per second, takes more than 8 minutes to reach Earth. Here, something subtle but important begins to change. Distance is no longer described primarily by how far something is in space. It is described by how long information takes to arrive. We stop thinking only in kilometers. We begin thinking in minutes. This shift is not philosophical. It is practical. Astronomers introduce new units, astronomical units, and light travel time, not because they prefer abstraction, but because older measures stop being useful. A commercial jet flying continuously would take nearly 20 years to reach the Sun. Even with technology far beyond what we currently possess, human travel becomes increasingly meaningless at this scale. Distance is still measurable, but it is no longer experiential. We can no longer imagine crossing it. Space begins to transform into time. And as we move farther outward, this transformation accelerates. The inner planets give way to the outer reaches of the solar system. Mars lies tens of millions of kilometers away, depending on orbital alignment. Jupiter orbits hundreds of millions of kilometers from the Sun. Saturn follows even farther out. Neptune circles the Sun at a distance of more than 4 billion kilometers from Earth. Sunlight takes over 4 hours to reach it. Already, intuition has failed. Distances are no longer something we imagine crossing. They are something we acknowledge mathematically. Travel becomes less about effort and more about feasibility. Even within our own solar system, size has outgrown human intuition. The solar system itself begins to feel less like a collection of destinations and more like a vast, sparsely populated region. And yet, even this is not the edge. Beyond the orbit of Neptune lies a realm of icy debris and distant objects, the Kuiper Belt, the scattered disk, and far beyond them, the Oort cloud, a vast spherical halo of icy remnants extending perhaps a light year or more from the Sun. At these distances, the Sun is no longer a dominant presence. Its light is faint. Its gravitational influence weakens. the solar system fades gradually into interstellar space. Beyond the influence of the sun lies the space between stars. Interstellar space. The nearest star system, Alpha Centauri, is more than 4 light-years away. That is over 40 trillion kilometers, a number so large that it no longer corresponds to any human experience. At the speed of our fastest spacecraft, the journey would take tens of thousands of years, not centuries, not millennia, tens of thousands of years. This is not a delay to be solved with better engineering. It is a boundary. Voyager 1, launched in 1977, is the farthest object humanity has ever sent into space. After more than 4 decades of continuous travel, it has only just begun to leave the sun's influence. It has not reached another star. It has not entered a new system. It is drifting through interstellar space, carrying with it a record of our existence. Voyager is not exploring the galaxy. It is marking the outer edge of what we can reach. At interstellar scales, distance reveals a hard truth. It is no longer a challenge to overcome. It is a limit. And it is here that the idea of size begins to fundamentally change. As we move farther outward, individual stars begin to lose their identity. What once appeared as singular points of light start to blur into patterns, into distributions, into structure. The Milky Way emerges not as a collection of destinations, but as a system, a vast spiral galaxy, roughly 100,000 light-years across, containing hundreds of billions of stars. Spiral arms curve gracefully around a dense central region. Between them lie immense clouds of gas and dust, slowly forming new stars over millions of years. Our Sun is just one star among many, orbiting far from the galactic center. From within the galaxy, its true scale is difficult to grasp, but from a distance, its size becomes undeniable. And yet, even within this immense structure, humanity occupies an astonishingly small region. Our physical reach extends only a tiny fraction of the distance between stars. Our technological presence is even smaller. The radio waves we have broadcast into space since the early 20th century have traveled only about 100 light-years from Earth. This expanding shell of information is known as the human radio bubble. It represents the farthest distance at which our existence could be detected by another civilization, assuming they are listening in the right way, at the right time. Beyond this boundary, the galaxy is silent, not empty, not lifeless, silent. Any civilization beyond this bubble would not know we exist, not because they are too far away in space, but because information has not reached them in time. At this scale, distance is no longer about travel. It is no longer even about space. It becomes about causality. What can influence us? What we can influence? What can ever be connected? Most of the universe is not distant in the way we usually imagine. It is causally disconnected. As we move beyond the Milky Way, the illusion of isolation disappears. Intergalactic space reveals itself not as a void, but as a structured expanse. Galaxies are not scattered randomly. They gather. They form small groups bound by gravity. These groups merge into clusters containing hundreds or thousands of galaxies. Clusters in turn arrange themselves along immense filaments, stretching across tens and even hundreds of millions of light-years. Between these filaments lie enormous regions of relative emptiness, known as voids. Together, these structures form what is called the cosmic web, a vast interconnected network that defines the large-scale structure of the universe. Our galaxy is not alone. It is part of a flow of galaxies moving together through space, drawn by gravity toward massive concentrations of matter. Superclusters emerge from this process, collections of galaxy clusters bound together across distances so vast that their very existence challenges earlier assumptions about cosmic uniformity. Some of these structures are among the largest known objects in the universe, so large that light itself takes hundreds of millions of years to cross them. And yet, even these colossal formations are not the whole story. Beyond them lies a boundary that cannot be crossed. Eventually, as we continue outward, we encounter a fundamental limit, the observable universe. It is a spherical region of space with a diameter of roughly 93 billion light-years. That number alone feels impossible. It immediately raises a paradox. If the universe is only 13.8 billion years old, how can it be so large? How can light have traveled such enormous distances in such a relatively short time? The answer lies not in motion through space, but in the expansion of space itself. Since the earliest moments after the Big Bang, space has been stretching. Not objects racing outward through a static void, but the fabric of space itself expanding everywhere at once. As space expands, the distance between galaxies increases, even if the galaxies themselves are not moving through space in the conventional sense. Over time, this expansion accumulates. Regions of space that were once relatively close become unimaginably distant. At sufficiently large scales, this expansion causes space to stretch faster than light can cross it. This does not violate the laws of physics. Nothing is moving through space faster than light. Instead, space itself is growing. The result is a cosmic horizon, a boundary beyond which light emitted today will never reach Earth. Not in a billion years, not in a trillion. These regions are not hidden behind a wall. They are separated by time itself. They exist beyond any possible causal connection. No signal sent today can ever reach them. No information from them can ever reach us. They are permanently inaccessible. The observable universe, then, is not the edge of space. It is the edge of what can ever be known. Everything beyond it may exist in abundance. Galaxies, stars, structures beyond imagination. But they are unreachable, unmeasurable, unverifiable. And it is here that the idea of size begins to collapse completely. At this point, the original question begins to unravel. How big is the universe? It sounds simple, but the more closely we examine it, the less meaningful it becomes. Because size, as we normally understand it, is not an absolute property. It is a relationship. It depends on where you are. It depends on how you observe. It depends on what information can reach you and what information never can. At small scales, size feels objective. A mountain is larger than a hill. A planet is larger than a moon. These comparisons hold because the entire system is accessible. But at cosmic scales, accessibility disappears. We cannot step outside the universe to measure it from the outside. We cannot observe it all at once. We cannot even confirm that what we see is representative of what exists beyond our horizon. What we call the universe is not the whole structure. It is a partial view, a region bounded by the speed of light, the age of the universe, and the expansion of space. Everything we observe is filtered through these constraints. Light must have had time to reach us. Signals must not be stretched beyond detectability. Events must still lie within our causal past. Anything outside those limits may exist just as vividly as what we see, but it cannot be measured, it cannot be confirmed, it cannot be placed on a map. At this scale, size stops being a physical quantity and becomes a property of observation. This is why different models of the universe produce radically different answers. Some suggest a finite universe, curved back on itself, with no true edge. Others suggest an infinite universe, extending endlessly beyond what we can observe. Still others propose structures far stranger than either: multiverses, inflationary bubbles, regions governed by different physical laws. But all of these ideas share a common problem. They describe realities that lie beyond observation. They may be mathematically consistent. They may be theoretically compelling, but they cannot be directly tested. And without observation, size loses its meaning, because size requires comparison. It requires boundaries. It requires the ability to say where something begins and where it ends. At the largest scales, we no longer have that ability. We exist inside a horizon, a boundary not marked by walls or edges, but by time itself. The farther away we look, the further back in time we see. At extreme distances, we are not seeing galaxies as they are now, but as they were billions of years ago. Eventually, we reach a point where the universe becomes opaque, before atoms formed, before light could travel freely, before structure as we understand it existed. Beyond that point, Even light cannot carry information, and beyond the observable horizon, not even theory can tell us what exists with certainty. This does not mean the universe ends there. It means our access to it does. The distinction is crucial. The universe does not need to be small or large in any absolute sense. It only needs to be structured in a way that limits what any observer can know. And those limits are built into reality itself. Speed, time, causality. These are not inconveniences. They are fundamental features of the universe. As a result, every observer, anywhere in the cosmos, occupies their own observational bubble, their own horizon, their own version of the observable universe. Two observers separated by vast distances will not agree on what exists now. They will not share the same past. They will not see the same future. Reality itself becomes relative to position, motion, and time, not in a subjective sense, but in a deeply physical one. From this perspective, the universe is not a single object waiting to be measured. It is a layered structure, a hierarchy of scales, each governed by its own limits. At small scales, size is tangible. At larger scales, size becomes abstract. At the largest scales, size dissolves entirely. What remains is structure, relationships, constraints, patterns of connection and disconnection. We are not explorers moving through an open, unlimited space. We are observers embedded within a system that reveals itself only partially. The universe is not hiding its size from us. It is structured so that size, beyond a point, is not a meaningful concept. This realization does not diminish the universe. It reframes it. Instead of asking how big the universe is, a more precise question emerges. What kind of universe produces horizons? What kind of structure limits knowledge in this way? What kind of reality allows complexity, galaxies, stars, planets, and observers to exist within finite pockets of information? In this sense, the observable universe is not a small fragment of a larger whole. It is a complete system from the perspective of any observer within it. Complete not because it contains everything, but because it contains everything that can ever matter to that observer. Beyond the horizon, existence may continue indefinitely, but it does so without interaction, without influence, without connection. And without connection, size becomes irrelevant. The universe does not need to be fully known to function. It does not need to be fully observed to exist. It only needs to be structured in a way that allows local order to emerge, structured in a way that allows information to flow, but not infinitely. It produces islands of causality in a vast, expanding whole. From within such an island, questions about absolute size lose their footing. They assume an external vantage point that does not exist. There is no outside observer. No cosmic measuring stick extends beyond all horizons. Only observers embedded within the system remain, each bounded by their own limits. Seen this way, the universe is not large or small. It is constrained. Those constraints are not flaws. They are what makes structure possible. They allow complexity to arise. They allow any question to be asked at all. So when we ask how big the universe is, we are really asking something else. We are asking how far knowledge can extend, how far influence can travel, how far connection can persist. And the answer is not a number. It is a horizon, a boundary defined by time, light, and expansion. Beyond it, reality may continue endlessly. But for us, and for any observer, that boundary is where size ends and structure begins.